Good afternoon, all of you. In last class, we discussed about definition of power electronics and different types of power electronic circuits and applications of power electronics in power system. And coming to first unit, the name of first unit is power semiconductor devices. So the rule of power semiconductor devices in power electronics is by acting these devices as switches. By acting these devices as switches, we can perform all power electronic operations like converting of electrical energy from AC to DC or DC to AC, or controlling of energy. If you take DC supply, we can increase its level. If you, as per our requirement, we can increase its level or decrease its level. Similarly, we can also perform all operations on AC to AC controllers by using these power semiconductor devices. And power semiconductor devices are heart of power electronic devices, because due to switching operations of power semiconductor devices only, we can perform all those operations. Next, coming to classification of power semiconductor devices. Power semiconductor devices are classified based on, first one is controlling, next one is based on blocking of input voltage, based on blocking of input voltage. Next, third one is based on direction of current flow, based on current direction
of current flow.
based on direction of current flow. Power semiconductor devices are classified into unidirectional and bidirectional. Unidirectional and bidirectional. Next, based on blocking, unipolar devices and bipolar devices. Unipolar devices and bipolar devices. Next, based on controlling, uncontrolled, semi-controlled, and fully controlled. These are the general classification of power semiconductor devices based on controlling, blocking, and direction of current flow. Next, we will consider certain parameters while choosing a any power electronics devices. So it means like mobile, we consider certain features like megapixel, screen resolution, processor, RAM, internal memory, like that. We can also consider some parameters while choosing a power semiconductor devices. The first one is voltage rating. Voltage rating means the maximum instantaneous voltage for which a device can block during its off state. A device can block during its off state. That much of voltage is known as voltage rating, and we need to consider this parameter to insert a particular device in a particular power electronic circuit. Next one is current rating. That is the maximum permeable level, that is the maximum capacity of the device. So the maximum allowable current during on state of the switch is known as current rating. That is the maximum rated current. Next, third one is switching speed. Switching speed. The speed at which a device can make transition from on state to off state, or off state to on state. That speed is known as switching speed. If the switching speed is less, the losses associated with power semiconductor devices is also less. Next, on state voltage. On state voltage. The voltage across the device during on state of the device. Whenever the device is in turn on state, the voltage which is appear across the switch. The voltage appear across the switch. Suppose in this case, if the switch is turn on, there will some voltage drop across the switch. That voltage is known as on state voltage. Next one is off-state current. Off-state current. Here, during off-state also some amount of current flows in the practical devices. Coming to ideal device, there is no flow of current, but coming to practical power semiconductor devices, there is some flow of current due to minority currents, and that current is in the range of some microamperes, not in milliamperes or amperes. It will be in microamperes. So due to that amount of off-state current also, there will be some power loss. So these 5 parameters will be considered while selecting any power semiconductor devices. And we discuss the difference between practical device and ideal device. This one is ideal power semiconductor device. This one is practical power semiconductor device. If we consider on-state voltage or during on-state of the device, during on-state of the device, voltage across the switch must be 0. Voltage across the switch must be 0, and the device must carry a large amount of current from minus infinity to plus infinity. But coming to practical device, during on-state, the voltage across switch will not be equal to 0. There will be some voltage drop across the switch. So VSW not equal to 0, and it will not allow every current. It will allow only some particular amount of current, and the range will be from it will be some from minimum value to maximum value. Next, coming to off state. During turn off state of the device, for ideal device there is no flow of current, but for practical device there is flow of some current across the switch. So ISW will not be equal to 0 for practical device, and for ideal device current flowing through the switch during off state equal to 0, and it should block minus infinity voltage to plus infinity voltage. So that is the range of ideal device. But practically, there is some limitations, and which will block some minimum amount to maximum amount. Beyond this limit, if we increase voltage, it could not block the supply voltage, and it acts as a conductors. So all of you know, insulators are semiconductors. Both will become conductor whenever we apply very large amount of voltage. This one is minimum voltage, and that one is the maximum voltage. Next, coming to switching speed. Switching speed for ideal device, there is no time to make transition from on state to off state, or off state to on state. So switching time is 0, but it will not equal to 0 for practical device. So if we do the variation of voltage, current, and power across the switch for ideal diode and practical diode, the waveforms are like this. This one is for voltage, and this one is for current, and this one is for power. Similarly, for practical device also, this one is for voltage, current, and this one is power. Voltage, current, power. Voltage, current. Here voltage means voltage across the switch, current flowing through the switch, and PL means power loss across the switch. So if you take ideal device, for ideal device, if you assume the device is initially in off state, if the device is in off state, it will block entire supply voltage. So this one is the entire supply voltage which is appear across the switch during off state. So when the switch is on, when the switch is on, the voltage when the switch on means it acts as a short circuit. Under short circuit condition, voltage across the switch equal to 0. Under short circuit condition, voltage across the switch equal to 0. So voltage will become 0 whenever the switch is turned on. Whenever the switch is turned on, voltage across the switch will become 0. And this one is off state. This one is off state and this one is on state, and it will not take any time to make transition from off state to on state. When if the device is turned on, the current, sorry, the voltage across the device falls to 0 due to flow of current at that moment. It will not take any time to change its state. Again, after some time, that if the device is turned off, it will block the entire supply voltage like this. Coming to current, whenever the switch is off, this one is the off state. So when the switch is off, current flowing through the switch equal to 0. Under open circuit condition, no current flows in the switch. So current equal to 0 like this. So when the device is turned on, so due to ideal property of the device, the current flowing through the switch increases suddenly like this. It will not take any time to reach its maximum current. The current will reaches its maximum value instantaneously. Again, when the device is turned off, it will not take any time to turn off. It means it will not take time to make transition from on state to this one is on state and this one is off state. It will not take time. So the current flowing through the device becomes 0 like this. So if you calculate power loss across the switch, the formula for power is product of voltage and current. During off state, current flowing through the device is 0 and there is some maximum voltage V. So V into 0, power loss is also 0. So this is the power loss across the switch. Next, during on state voltage is 0 and there is some maximum current I. So in this case also power loss is 0. So for ideal device, there is no power loss across the switch. Coming to practical devices. Initially assume the device is in off state. So voltage across the switch equal to supply voltage V like this. This one is the supply voltage V. So whenever the switch is turned on, either diode or SCR, whenever the switch is turned on, it will take certain time to turn on to make the transition from off state to on state. It will take certain time. So during this process, voltage across the switch decreases like this. And voltage does not equal to 0 even to the device is turned on because there is some on state voltage across the switch. For practical device, there is some on state voltage like this. This one is on state voltage. So again, this one is here. This time is known as here the device make transition from off state to this one is off state and this one is on state. This one is transition time. So transition time or transient time, all of you know the definition of transient response. The response of the system when it changes from one stable state to another stable state. This off state is one stable state and this on state is another stable state. So here the system makes transition from this stable state to this stable state. So this is transient response of the system. So this one is turn on time. This one is turn on time of the device. This is the turn on time of the device. It will take certain time to make transition from off state to on state. So coming to current, under open circuit condition also there will be some flow of very small amount of current. For ideal device there is no current, the current is zero in off state, but for practical device there is some small leakage amount of current like this. So at this point when the switch is turned on, the current does not increase instantly like this as ideal device. It will take certain time to reach maximum value like this. The current increases gradually like this. Here the current increases gradually. So after turn on, the current becomes maximum value. Next, again, at this point, if you want to close the switch, if you want to open the switch, just remove the gate signal, then it will again take certain time to turn off the device. It will take certain time to make transition from on state to off state. So the voltage across the device gradually increases like this, and again after a certain turn off time, it will become constant like this. But coming to practical device, it make transition instantaneously. The voltage across the device increases instantaneously like this. But for practical device, it will increases gradually like this. This time is known as turn off time. This one is turn off time. This one is off time. This time is on time. On time of the device. This time is off time of the device. So if voltage increases, if the device or turn off, the current flowing through the device gradually decreases like this. It will not become zero instantaneously like ideal device. It will take certain time to become two decreases, and it will not equal to zero. So there is some small amount of current flows like this. So these are the waveforms of current and voltage for practical device. Coming to power. So you know the formula for power. The formula for power is product of voltage across the switch and current flowing through the switch. So there is some during off state, it only the voltage is maximum voltage and some minimum amount of current flows in the device. So product of this current and voltage is like this. So this one is power loss across the switch. So in this condition, during turn on time of this switch, the voltage across the device gradually decreases and current gradually increases. So power loss will be like this. So again, during on time of this switch, during this one is the on time of this switch or the steady state response. During steady state response, the current voltage is like this and current is maximum value. So due to multiplication of these two values, we get the value of power like this. Again, this one is turn off time. During turn off time also, voltage gradually increases across the switch and current flowing to the switch gradually decreases like this. So the power loss is like this. So here, these losses, the losses in off state and on state due to flow of current or steady state losses are known as conduction losses. This losses plus this losses is known as conduction losses, and transient losses. This one is transient losses. These losses are known as both turn on and turn off losses. These losses are known as switching losses. So total power loss across the switch equal to sum of switching losses and conduction losses. So comparing to conduction losses, the amount of switching loss is more. It is also very important for competitive exams. In case of power semiconductor devices, which losses are high? Switching losses or conduction losses. So switching losses are more comparing with conduction losses for power semiconductor devices. So this is the comparison between ideal power semiconductor devices and practical power semiconductor devices. Any doubts about this one?
No, sir.
Okay. So now we will consider the difference between normal diode and power diode. Normal diode. What is the difference between conventional electronics and power electronics? What is the difference between conventional electronics and power electronics?
Power electronics are used at high ratings, sir. High power
Power
ratings.
electronics are used for high power applications or high power ratings. And conventional electronics are used only for low power applications. So if you take the ratings of normal diode, normal conventional diode, the current rating will be some 0.5 amps. This one is the maximum current carrying capacity of the normal diode. Coming to voltage rating, it will be some 0 to 5 volts. So here it means the maximum current carrying capacity of the diode during on state is 0.5 and maximum blocking capacity of the device during off state. So this is the ratings. So it means it can block 5 volts voltage and it can carry 0.5 amperes of current. These are the ratings of normal diode, and so due to these low ratings, it can be used only for low power applications. Coming to power rating. So for power diode, we need to carry kiloamperes of current during on state. So then only we can use these devices for power system. If you take a transmission system, if you need to use diode, the diode must be capable of carrying kiloamperes of current. Next, during off state, it should be capable of blocking kilovolts of voltage. So these are the requirement for power diode. So here we need to improve the ratings of the diode. So here the parameters for which a diode can depends is the off state or blocking voltage of the device depends on the width of the deflection layer. Suppose if you take a diode, the off state blocking voltage of the device depends on width of depletion layer. Width of depletion layer. So the blocking capacity depends on width of deflection layer and charge carrier density. Charge density. So if you want to block high amount of voltage, if you want to block high amount of voltage, the width of the deflection should be more and charge density must be less. Then only we can block very high voltage. Next one is if you want to allow very large amount of current. If you want to allow very large amount of current, the width of the deflection layer should be low and the charge density must be high, then only we can allow very large amount of current during on state. Suppose if the charge density is very less, charge density very less means the device offers very high resistance or high impedance. If it offers high impedance, more losses across the switch. So during on state, the charge density must be high, and during off state, the charge density must be low, and the deflection layer width must be high. Then only it can block very high amount of voltage. Suppose if you take the construction of diode, diode is formed by the joining of two eccentric semiconductors like p-type and n-type. This one is p-type material and this one is n-type material, and the majority carriers in p-type material are holes, and majority carriers in n-type material are electrons. So under normal operating conditions, the electrons near to the junction is diffused to p-type material, and the holes near to the junction diffused to n-type material, and forms a layer around the junction. So due to this diffusion of electrons and holes, there is some electric field or some negative voltage appears across this region. Like this one is the barrier voltage, and the diffused holes and electrons from either side will block further diffusion of electrons and holes. The holes which are diffused from p-type here opposes the further diffusion of holes from p side, and the electrons which are diffused into p-type opposes further diffusion of electrons from this n-type, and this one acts as a barrier. Suppose if you apply reverse bias, here it is p and it is n. Reverse bias means p-type region is connected to negative and n-type region is connected to positive. So here electrons are attracted like towards p plate and holes are attracted negative plate. So there will be some space created in p region, and there will be some phase created in region due to diffusion of electrons towards positive plate and negative plate, and so some of the electrons are moved to this region and some of the holes moved to this region. So width of the deflection layer increases in reverse bias condition, and it should block the supply voltage. This one is the supply voltage. If we increase this voltage further, there is some breakdown occurs in the junction, and it acts as a conductor. So in reverse bias condition, the current flows due to minority carriers like this, and after breakdown, the current increases like this. So it acts as a conductor, and it should not block further increasing voltage. It will block up to breakover voltage. If we increase this input voltage, the device gets damaged and acts as a insulator. So this can be avoided by decreasing charge density. Suppose if you decrease charge density, we can increase the rating of the device. If you decrease charge density decreasing means it acts as nearly insulator. It acts as nearly insulator, so it should be capable of blocking high voltage. And the width of the deflection layer also increases due to reverse bias condition. If you deflection layer width increases and the charge density decreases, then it should be capable of blocking high voltages. So it satisfies our first requirement of blocking high voltage. This can be achieved by decreasing doping concentration and increasing depletion layer width. So if the same device is used in forward bias condition, if the same device is the diode or device is used in forward bias condition. In forward bias condition, our requirement is the diode must allow large amount of current without any losses. So during forward bias condition, here the same device is used in forward bias condition. So here the charge density is decreased. So number of charge carriers available in p-type and n-type are reduced. And there is some small depletion layer, and it will be overcome after cut-in voltage or threshold voltage, and current starts flowing. Here the current flowing through the device is very low due to less charge density, and the power loss across the device is also high due to high impedance offered by this one because of low charge density. So if we decrease charge, if we decrease charge density, if we decrease charge density means if we decrease doping level, we can achieve only one state. It means the device can block high voltage, but it should not allow high current. It satisfy only one condition. It satisfy only one requirement. It does not satisfy other requirement. So suppose other requirement is we need to allow high current. To allow high current, we need to increase the doping level. So here just P minus notation means less doping. P means moderately doping. P plus means heavily doping, highly doping. P plus means high doping. Here we take the case of lightly doping case. This one is P minus and this one is N minus. Now we take the case of highly doping case, P plus. This one is P plus and this one is N plus. So during forward bias condition, due to increased charge density, it will allow very large amount of current, and it offers very low impedance. So power loss across the device must be low. So it satisfies the first requirement, that is it allows very large amount of current. If you use the same device in reverse bias condition, if you use same device in reverse bias condition, this one is P plus, this one is N plus. So during reverse bias condition, the width of the deflection layer increases. So it should block a certain voltage. But if we increase this voltage further, due to high charge density, breakdown occurs at a lower voltage. Breakdown occurs at a lower voltage, and it allows the flow of current. So it acts as a conductor at lower voltage. So it should not block high voltage if we increase doping level. And if we decrease doping level, it should not carry high currents. But we need to satisfy these two requirements in a single device. We need to satisfy these two requirements in a single diode. How can we achieve this? How can we satisfy these two conditions in a single device? So this can be done by introducing another layer, in between P layer and N layer. So this one is normal P layer, and this one is N layer. Here, in order to allow very large amount of current, N layer is highly doped. And to block very high voltage in reverse bias condition, N minus layer is introduced in between P layer and N layer. That is the difference between normal diode and power diode. In power diode, there is extra layer in between P layer and N plus layer. It means N layer is divided into two parts. One part is lightly doped and other part is heavily doped to achieve two conditions. Like high current carrying capacity and high voltage blocking capacity. These are the requirements of any switching device. The switching device should block high voltage during off state and it should carry high current during its on state. These are the requirements of every switch. So if we apply forward bias, this one is negative, this one is positive. Here volts repel with this positive plate and move to this N region. And here highly doped electrons move to N minus region electrons. So due to this neutralization process, the entire layer acts as a conductor and the device allows very large amount of current during forward bias condition. So it satisfies our requirement of high amount of current during on state. Suppose during reverse bias condition. Hello, all of you please mute your mics. So during reverse bias condition, this one is P, this one is N plus, and this one is N minus. So during reverse bias condition, here this one region N minus region is very lightly doped. So charge density is very less. So due to applied voltage, if you increase this applied voltage, the reverse charge carriers are diffused more. So here it is the depletion layer and holes are moved like this. And some of the electrons moved like this. So it means majority of the depletion layer is diffused to N minus layer. So here depletion layer with increases and charge density decreases. So should be capable of blocking high voltage. So like this, by introducing this layer, we can satisfy both the conditions during on state and off state. This concept is used in SCR. The same concept is used for SCR to block high voltage and to carry high current during on state and off states respectively. So coming to SCR. So the full form of SCR is silicon controlled rectifier. As it performs rectification operations, these devices are called a silicon controlled rectifier. So coming to construction of SCR, what is the what you know about SCR? Tell me anything about SCR. All are studied in our diploma about SCR. What you know about SCR?
Unit control device.
Semi-controllable device. Very good. Semi-controllable. Based on controlling, it is a semi-controllable device. Next, based on blocking, SCR is a SCR can block both the polarities of voltage. So during reverse, suppose if you apply sine wave during negative half cycle, it is reverse bias, so it blocks negative half cycle. During positive half cycle also, it will not turn on. It will be in forward bias only. It will be in forward blocking mode. In forward blocking mode also, the device acts as a off switch. In negative half cycle, it acts as a off switch. So it blocks both positive polarity and negative polarity. So it is a bipolar device. Bipolar. Next one. It is a semi-controllable device. It is a bipolar device. Next one, unidirectional device. It allows flow of current only in one direction. Unidirectional device. Next, how many layers are present in SCR? Total
Four,
number
sir.
of 4 layers. So this one is P, N, P, N. Total 4 layers present. So it is a 4 layer. How many terminals are there in SCR? Number of terminals in 3.
Three, sir. Anode, cathode, gate.
Anode, cathode, gate. And gate is connected to which layer? P layer. This one is gate. So 4 layer, 3 terminals, 3 junction device. This one is junction 1. This one is junction 2. And this one is junction 3. Next, coming to doping. So here we have 4 layers, 2 P layers and 2 N layers. Here P layers, both P layers are moderately doped regions. Both regions are moderately doped regions. And remaining N layers, here we have 2 N layers. One is N plus, another one is N minus. This one is N minus. This one is N minus. And this one is N plus. So to allow very large amount of current during on-state, one layer is highly doped like this. This one is N plus, and to block high amount of voltage during off-state, one layer is lightly doped. This one is N minus. So out of 4 layers, which layer is responsible for blocking high amount of voltage? Which layer is responsible for blocking high amount of voltage? First layer, second layer, third layer, or fourth layer? Hello? Once again, I repeat the question. Out of 4 layers, first layer, second layer, third layer, fourth layer, which layer is responsible for blocking high voltage? Not third layer, second layer. Second layer is lightly doped. Lightly doped means charge density is less. If charge density is less, it acts as insulator. If it acts as insulator, it blocks high amount of voltage. Next, after 4 layers, which layer is responsible for carrying very high amount of current? Fourth layer. Due to highly doped region. This one is N plus. This one is N minus. Next, coming to operation. So operation of the SCR is explained in 3 modes. What are the different modes of operation of SCR? First mode, reverse block.
Conduction.
Okay, that is also one of the mode of operation of SCR. Reverse blocking mode.
Saturation mode.
So reverse blocking RBM. RBM means reverse blocking mode. Next mode,
Forward blocking mode.
Forward blocking mode. Forward blocking mode. So FBM. Third mode, forward conduction mode.
Conduction mode.
Forward FCM. So during a reverse blocking mode, the SCR acts as on switch or off switch?
Off state, sir.
Off state. Next. During forward blocking mode,
Off state, sir.
off state. During forward block conduction mode, it acts as
On
state. So first we check the reverse blocking mode. RBM. Okay, in reverse blocking mode, the SCR is applied by reverse bias. This one is P, this one is N, this one is P, and this one is N. So to make it reverse bias, P is connected to negative terminal and N is connected to positive terminal. So here the polarities of voltage is like this, minus plus. So same way voltage appears across each junction. This one is J1, J2, J3. The voltage across J1 is like this, minus plus, and J2 is minus plus, then J3 is minus plus. So here the device is said to be reverse bias if P is connected to negative and N is connected to positive. So here junction J1 is forward bias or reverse bias?
reverse bias, sir.
Reverse bias, because negative is connected to P and positive is connected to negative. So it is a reverse bias. Next, junction J2.
Forward bias.
Forward bias. Because N is connected to negative supply and P is connected to positive supply. Next, junction J3.
Reverse bias.
Reverse bias. So here junction J1 and J3 acts as reverse bias. So if it acts as reverse bias, it means these two are open circuited. This one is junction J1 and junction J2 is forward bias. Forward bias means it acts as a short circuit. And this one is junction J3. Junction J3 is also acts as open circuit. And so here okay, N minus layer is lightly doped region, so it will take the complete responsibility of blocking high amount of voltage. So here N plus region is not responsible blocking a high amount of voltage. At lower voltage also, after if you increase the voltage after certain value, it acts as a short circuit after certain voltage. If you increase, but it will still act as a open circuit. So the blocking capacity of input voltage is taken by junction J1. So this is the operation of SCR during reverse blocking mode. And if you draw the characteristics of SCR in reverse bias condition, this one is current flowing through the switcher SCR ISW, and this one is the voltage across the switch. So in reverse bias condition also some amount of current flows in the switch due to minority carriers like this. This one is in microamperes. And whenever if we increase the voltage across the switch, after breaker voltage, the SCR gets damaged and current increases suddenly like this. So this point is known as VBO, VRBO, reverse breakover voltage. So here VRBO means reverse breakover voltage, and it is defined as the maximum voltage across this switch in reverse bias condition at which the current flowing through the device increases rapidly. So this one is reverse breakover voltage, VRBO. Next, coming to forward blocking mode. This one is PN, PN. This one is minus, this one is plus. So in forward blocking mode, anode is connected to positive and cathode is connected to negative. So the polarities of supply voltage is like this, plus minus. This one is junction J1, junction J2, junction J3. So the voltage across junction J1 is plus minus. This one is also plus minus. This one is also plus minus. Here plus is connected to positive and minus is connected to negative. So junction J1 is forward bias.
Forward bias, sir.
Forward bias, very good. Next, coming to junction J2.
Reverse bias.
Reverse bias.
Junction J2 is reverse bias because positive is connected to negative, negative is connected to p-type region. So it acts as a reverse bias. Next junction J3 is forward bias. So junction J1 acts as short circuit. Junction J2 is reverse bias, so it acts as open circuit. So junction J3 also acts as a short circuit. These two junctions are closed switches and junction J2 is open switch. Suppose if we increase input voltage, this one is Vs or input voltage. If we increase Vs beyond VBO, this one is we have forward breakover voltage. Up to this point, the device acts as open switch. Up to this point, if the supply voltage is less than VBO, if the supply voltage is less than VBO, the device acts as off switch due to reverse bias of junction J2. If we increase supply voltage beyond VBO, the junction, the depletion layer at the junction J2 decreases. If the width of the depletion layer at the junction J2 decreases, it starts conduction and it will be turned on. So this happens only when supply voltage Vs increases, VBO, forward breakover voltage, and the device is turns on, and this mode is forward conduction mode. This one is forward conduction mode. So this one is the supply voltage and current flowing. There is also some amount of current flows in forward blocking mode. This one is small amount of current. This one is VBO, forward breaker voltage. If the voltage is increased beyond VBO, the device gets turned on. So the device is turns on. If the device is turns on, voltage across the switch is, if you under short circuit condition, voltage across the switch is 0. So voltage drops to like this and current increases like this. So with increasing supply voltage, voltage across the switch is constant. There is some on state voltage 1.5 volts. For SCR, the voltage across the switch during on state is 1.5 volts. For diode, it will be nearly some 0.7 volts. So this constant voltage appears across the switch. With increasing supply voltage, with increasing VS, if increases IS, anode current or switch current IA increases like this. But the voltage across the switch, here VSW means voltage across the switch, not supply voltage. Voltage across the switch is constant once the device is turned on, and current flowing through the device increases like this. So before turn on of the device, the voltage across the switch is supply voltage. So this one is all the voltage is supply voltage. And if the supply voltage is beyond breakover voltage, it starts conduction and voltage across the switch falls to some 1.5 volts. And with increasing supply voltage, current flowing through the anode increases. So current flowing through the device increases, which is nothing but anode current. These are the three states of SCR. So all of you know the definitions of holding current and latching current. What is holding current and what is latching current? I think all of you hear these two terms. Anyone please tell me what is latching current and what is holding current? Are you here or not? It is, these two definitions are very, very important. What is holding current and what is latching current? So IL, IH. IL means latching current. IH means holding current.
Holding current means minimum current passes through the circuit, sir.
Minimum current passes through the circuit. When it passes through the circuit, during on state or off state?
Off state, sir.
Off state. On state.
On state, sir.
On state. What about latching current?
Maximum current. Maximum current in the circuit.
Maximum current flowing through the circuit. So somewhat correct, but not exactly right one. So coming to latching current. So latching current means the minimum amount of current flowing through the device to turn on the device. The minimum amount of anode current at which the device turns on. That minimum amount of current during on state is known as latching current. Is it clear? Minimum amount of anode current to turn on the device. The minimum amount of anode current to turn on the device is known as latching current. So holding current means the minimum amount of anode current below which the device gets turned off. If we decrease anode current below IH, if anode current is less than IH, if the anode current is less than holding current, the device gets turns off. So this one is holding current is related to off state of the device. This one is related to off state of the device, and latching current is related to on state of the device. Is it clear? So once again, I repeat the definitions of latching current and holding current. Latching current means the minimum amount of anode current. Suppose this one is the SCR. The minimum amount of current required to turn on the device. That current is known as latching current. So if it will not reach that current, the device gets turned on. The device will not turn on. So that is minimum amount of anode current at which the device turns on when the gate signal is removed. So when the gate signal is removed, the minimum amount of anode current at which thyristor gets turned on is known as latching current. So coming to holding current, the minimum amount of anode current below which it will be turns off. If the anode current is decreased below holding current, the device will be in turn off state. So holding current is related to off state and latching current is related to on state. Both the values are nearly same, but comparing with holding current, latching current is more. So to turn on the device, we need somewhat more current. So to turn off the device, we need some minimum amount of current. Both currents are minimum, but this one is related to on state and this one is related to off state. Any doubts? Hello?
No, sir.
No, sir.
Okay.
No, sir. Time is going, sir.
No, sir.
Up to 4 o'clock and 2 to 4. So coming to finger voltage. Finger voltage. This definition is not important, but you need to know about finger voltage. Finger voltage means the minimum amount of voltage across the switch. The minimum voltage, the minimum amount of voltage across the switch to turn on the device. That voltage is known as finger voltage. It is same as breaker voltage. So the minimum amount of voltage required to turn on the device is known as finger voltage. Next, turn on methods of SCR. Turn on methods of SCR. First one is forward voltage triggering method. Forward voltage triggering. Next method, dV by dt triggering. The turn on methods of SCR are very important. Next method, dV by dt triggering. Next method, light triggering. Next method, thermal
Gate
triggering.
triggering, sir.
Last method, gate triggering. Thermal triggering. Next last method, gate triggering. Out of 5 methods, which method is preferable?
dV by dt, sir.
dV by
dV by
dt.
dt.
There is some damage of your device. There is a chance of damage of device due to high change in voltage.
Gate triggering, sir.
Gate triggering is best method out of 5 methods, and it is safest method. So forward voltage triggering means we cannot apply any gate signal to the device. So the supply voltage is more than here. This one is the supply voltage. If supply voltage is more than VF breaker voltage, then during forward bias condition, J1 forward bias, J2 reverse bias, and here it is J2 and it is J3. J2 is reverse bias condition. So if you apply supply voltage beyond forward breaker voltage, the width of the depletion layer at junction 2 decreases, and it acts as a short circuit, and it allows flow of current. This method of turn on of SCR is known as forward voltage triggering method. Next method is dV by dt method. So here junction J2 is reverse bias, so it acts as a capacitor. What is the formula for current flowing through the capacitor? What is the formula for current flowing through the capacitor? What is the formula for voltage across inductor? Take inductor is supplied by some voltage. Voltage across inductor. Phi is the current flowing through the inductor, and inductance value is L. So what is the formula for voltage across inductor? VL equal to L into di by dt. The formula for voltage across inductor is VL equal to L into di by dt. In the same way, what is the formula for current flowing through the capacitor?
C into di by dt, sir.
C into dV by dt. Current flowing through the capacitor equal to C into dV by dt. So capacitor means two plates separated by some distance, and here this one is capacitor, and the medium between the two plates acts as a dielectric medium. This one is the capacitor, and current flowing through the capacitance is IC equal to C into dV by dt. Here also the depletion layer region, the polarity of depletion layer is minus, 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 plus, plus, plus. And junction J2 acts as a dielectric medium. So here this one completely acts as a capacitor. So the amount of current flowing through the capacitor formula is IC equal to C into dV by dt. So in order to increase this current, we need to increase change in voltage. So if we apply change in voltage, the amount of current flowing through the capacitor increases. So if it is the minimum amount of current, so the minimum amount of current required to turn on the device is latching current. So this one is IL. So if IC is equal to IL, then only that device gets turned on. This one is capacitor current. If capacitor current is equal to IL, IL is latching current, then it will be turned on. So IL equal to C into dV by dt. So if you know the value of latching current and capacitance, if you know the value of latching current and capacitance of the junction J2, you can calculate critical voltage, the voltage required to turn on the device, dV by dt equal to latching current by capacitance value. This is also very important formula. The minimum amount of change in voltage required to turn on the device, dV by dt equal to latching current by capacitance. So like this, we can turn on the SCR. Next method is light triggering method. So whenever the light is applied at junction J2, due to energy present in the light, the junction J, the width of the depletion layer width of the junction J2 decreases, and it starts conduction due to light energy which is projected at junction J2. Next, coming to thermal triggering method. So in thermal triggering method, the formula for here IA means anode current. The formula for anode current is alpha 2 Ig by IC B1 plus IC B2 by 1 minus alpha 1 minus alpha 2. Here anode current increases either with increasing gate current or with increasing ICB1 and ICB2. Here ICB1 and ICB2 are reverse leakage current, and these reverse leakage currents are increased with increasing temperature. So whenever if you increase temperature, ICB1 and ICB2 increases. If ICB1 and ICB2 increases, anode current increases. Like this we can turn on SER. Next, coming to gate triggering method. Gate triggering methods are again two types. One is pulse triggering method. Next one is continuous triggering method. In pulse triggering method, we need to apply a pulse up to turn on of a SER. So this one is if it is the turn on time. So if it takes certain time to turn on the device, the width of the pulse is like this. Up to that point, the pulse is present. After once the device gets turned on, if you remove the gate pulse, it will be still in conduction state. If you apply continuous triggering, continuous gate pulse, it will be present during on state. It will be present during entire on state of the device. But in pulse triggering method, it will present up to turn on of the device. Once the device gets turned on, it will be removed in the pulse triggering method. But in continuous triggering method, the gate will be applied continuously. So due to this, the power loss across the gate will be increased. So after these two methods, pulse triggering method is preferred. So the power loss and the SCR is less in pulse triggering method. So it will be preferred. These are the general triggering methods are terminal methods of SCRs. Next topic is two transistor analogy of a SCR. Two transistor analogy ANALOGY. Two transistor analogy of SCR. So if you take the construction of SCR, SCR consists of 4 layers. This one is P layer, this one is N layer, and this one is P layer, and this one is N layer. So it is anode, this cathode, this gate. So here gate current IC, anode current IA, cathode current IK. So if you apply KCL, what is the relation between IA, IC and IK? What is the relation between IC, IK and IK? Here incoming currents are IA, IC. Outgoing current is IK. Then what is the relation between IA, IC and IK? Hello? Anyone please respond?
Sir.
Here incoming current is IA and IC. outgoing current is IK. What is the relation between IJ, IE and IK if you apply KCL? What is KCL? Incoming currents equal to sum of incoming currents equal to sum of outgoing currents. So IA plus IZ equal to
IK.
IK. So if you observe the 4 layers, the 3 layers, the first 3 layers acts as a PNP transistor. This one is PNP transistor, and these 3 layers acts as NPN transistor. These 3 layers acts as PNP transistors, and these 3 layers acts as NPN transistor. If you divide these 2 layers into 2 parts, this one is P, this one is N, this one is P. So this one is N, and this one is P, and this one is N. So here gate currents are like this. This one is IA, and there is a connection in between N and N, P and P, and this one is cathode K. The current flowing through the cathode is IK, and this one is gate, and gate current is IZ like this. So here it is PNP transistor and it is NPN transistor. All of you know very well about the transistors. The symbol of PNP transistor is like this. This one is PNP transistor. This one is NPN transistor, and this current is IE, and this current is the direction of currents in PNP transistor is like this. This one is emitter current. This one is emitter current IE, and this one is base current IB, and this one is collector current IC. So here the relation between IB, IC and IE is IB, IC and IE. So incoming current IE, outgoing currents IB and IC. So IG equal to IB plus IC. Similarly for NPN transistor, this one is IC and this one is IB. Just the direction of current changes in NPN and PNP transistors. So in this case also IE equal to IE is outgoing current for NPN transistor, and IB and IC are incoming currents. This one is IB and this one is IC. So if you draw this structure in the form of symbols, this NPN transistor is like this. So this one is cathode current IK. This one is transistor 1. This one is the first transistor is PNP transistor and second transistor is NPN transistor. First, this one is the NPN transistor, then this is second transistor. And gate current is connected, gate is connected to NPN transistor. So this one is gate and gate current is IK. So here the terminal is emitter terminal. This terminal is collector terminal. As it is second transistor, the current is represented as IC2. Hello. So this one is IC2 and this one is IB2. This one is base current to the second transistor is IB2 and collector current to the second transistor is IC2 and the collector current is IE2. So this one is second transistor and this one is first transistor. For first transistor, here N layer acts as base and E layer acts as emitter because the direction of current is from this terminal to next. This current is flows through the this terminal, and this terminal. So this one is emitter and this one is base and this one is collector. So this one is PNP transistor. So here base is connected to this IC2. This current is IB1. This is the base of PNP transistor. Next, this current is IC1. And this is connected to IB2. Because it is connected to a base of NPN transistor. The collector of PNP transistor is connected to base of NPN transistor like this. So yeah, this terminal is connected to base of NPN transistor like this. And gate is also connected to this terminal. This one is gate current. This one is IG, this one is IK. And anode is connected to P of first transistor. So it means emitter. This one is anode current IA. So for first transistor, this one is this current. This current is IE1. This current is IE1. This one is IC1. This one is IB2, and this one is IC. From this figure, what is the relation between IB1 and IC2? Both currents are same. IB1 equal to IC2. IB1 equal to IC2. And next, IA equal to IE1. IA equal to IE1. Next, IE2 equal to IK. So here IK equal to IE2. Next one is IZ equal to next relation is IZ equal to IC1 plus IB2. Sorry, IZ plus IC1 equal to IB2. IZ plus IC1 equal to IB2. So all of you know the formula for current gain. Alpha equal to in common base. The formula for current gain is alpha equal to IC by IE. So if you take for transistor 1, it will be current gain will be alpha 1. So from that collector current IC1 equal to alpha 1 IE1. IC equal to alpha into IE. For transistor 1, IC1 equal to alpha 1 into IE1. If we consider common base leakage current, this one is the leakage current. IC B0 1. This one is leakage current due to transistor 1, and it is the formula for collector current. So if you take transistor 1, so what is the relation between IE and IB, IC? So here IE equal to IB plus IC. So from that IC equal to IE minus IB. IE equal to IB plus IC. From that IC equal to IE minus IB. IC equal to IE minus IB. Here for first transistor IE1, IE1 equal to alpha 1 IE1 plus ICB 01. So if you bring this alpha 1 IE1 to left side, IE1 is common. IE1 is common term in common in both the terms. So IE1 into 1 minus alpha 1 minus IB1. This one is IB1. I see B0. From that IB1 equal to IB1 equal to 1 minus alpha 1 into IE1 minus IC B0. IC B0 1. So if you observe this two transistor analogy, if you observe the diagram of two transistor analogy, okay, some part of the diagram is missing here. Okay, now it is okay. So here IB1 equal to IC2. So substitute IB1 equal to IC2. This one is IC2. This one is 1 minus alpha 1 into IE1. What is the relation between IE1 and other parameters? Is there any relations here? IE1 equal to IA. Both currents are same. IE1 equal to IA. So substitute this value. This one is IA. Minus IC B0. So here IC2 is second transistor collector current. So what is the relation between collector current in terms of common base gain? In terms of gain, if you take for second transistor, alpha it equal to IC2. IC2 by IE2. This one is the formula for current gain of second transistor, alpha 2 equal to IC2 by IE2. From that collector current for second transistor, IC2 equal to IC2 equal to alpha to IE2. Alpha to IE2. This one is the formula for IC2 without leakage current. If you consider leakage current, it will be equal to IC B02. It will be equal to alpha to IE2 plus IC B02. Substitute this value in this equation. Substitute IC2 value equal to alpha to IE2 plus I0B2. So alpha to IE2 plus ICB02 equal to 1 minus this one 1 minus alpha 1 IA minus ICB1. This one is ICB01. So next, here it is the IE2. IE2 means IE2 equal to IK. IE2 equal to IK. Alpha 2 IK plus ICB02 equal to this equation. Next, if you check the relation between IK anode current and gate current, IK equal to IA plus IZ. Substitute this equation in IK value. Alpha 2 IZ plus IA this one, this term is this one. Next, take this IC B0 to right side. So the remaining value is 1 minus alpha 1 IA minus IC B0 minus this one is plus IC B0 becomes minus IC B0 right side. IC B02. So in these two terms, IA is common. So if you multiply with alpha to IZ plus alpha to IA, in these two terms, IA is common. If you take IA common, then equation becomes IA into this one is take this term alpha IA to right side. Alpha to IA to right side. Then the remaining equation is IA into 1 minus alpha 1 minus alpha 2. And these two terms to right side. Here the remaining value is alpha to IZ. Alpha to IZ plus IC B01 plus IC B02. So from that anode current IA equal to this value by 1 minus alpha 1 minus alpha 2. So from this expression, with increasing gate current, we can increase IA. So with increasing gate current, we can turn on the device. This one is one of the method of turn on of a SCR. Next method is with increasing IC B01 and ICB02 reverse leakage current. These reverse leakage current are increased by increasing temperature. If temperature increases, these two currents increases. Whenever these two currents increases, IA increases. Though this one is thermal triggering method and this one is gate triggering method. And this complete analysis is known as two transistor analysis of SCR. This one is also very important question. Any doubts? Any doubts about this topic?
No, sir.
Okay, next. Already we discussed static characteristics of SCR. So if you take this graph with increasing gate current, so with increasing gate current, we can decrease breakover voltage. It means here breakover voltage means the voltage at which the supply voltage at which thyristor turns on is known as breakover voltage. This breakover voltage will be reduced by applying gate signal. If we apply gate signal at lower voltage, at lower supply voltage, the thyristor turns on. So this one is new voltage due to applying gate signal IZ. This one is due to gate signal IZ1. This one is new breakover voltage VB1. So then the direction of current is like this. If we increase the gate current, so it means IZ2. If we increase, if IZ2 is greater than IZ1, the SCR gets turned on at lower voltages. So then the voltage will be reduced. Then the supply voltage at lower voltage also the gate will be, so the SCR will be turned on. So with increasing gate signal at lower supply voltage also we can turn on the device. These are the static characteristics of SCR, and these characteristics does not depend on time. Next type of characteristics is dynamic characteristics. So the other name of dynamic characteristics is switching characteristics. Switching characteristics is also known as dynamic characteristics. And the dynamic characteristics are classified into two types: characteristics during turn on state and characteristics during turn off state. So these are the switching characteristics. Switching characteristics are dynamic characteristics. So other name of switching characteristics is dynamic characteristics. These characteristics are classified into two types: turn on characteristics and turn off characteristics. Next, turn on characteristics are divided into three parts. First part is during delay time, TD. Next, during rise time, TR. Next time is TP or TS setting time. This one is delay time. This one is rise time, and this one is setting time. Next, turn up time is also divided into two types: reverse recovery time TRR plus TGR, gate recovery time. So turn off characteristics are divided into two types, and turn on characteristics are divided into three types: delay time, rise time, and setting time. This one is reverse recovery time, and this one is gate recovery time. These are the switching characteristics of SCR. Switching characteristics are dynamic characteristics. First, we check the switching characteristics during turn on. So turn on characteristics, delay time, rise time, and setting time. So here delay time means delay time TD. So delay time is defined based on voltage across SCR, current flowing through the SCR, and gate
బిల్లు
signal.
కట్టకుండా
Hello?
నెట్ అవుతుంది నెట్ కూడా ఫాస్ట్ గా అవుతుంది ఒకసారి అవుతుంది
So delay time in terms of gate signal, in terms of gate current, delay time is defined as time taken by the gate current to reach 90%. Time taken by the gate current to reach 90% of maximum value. This time is known as delay time. In terms of anode current, it is defined as time taken by the response to increase to 10% of maximum current. Suppose if the anode current reaches 10%, then the time taken to reach 10% of maximum current is known as delay time. Next one is in terms of voltage, in terms of anode voltage. VAK. So time taken by the voltage across the switch to drop from 100% to 90%. So these the time taken for gate signal to reach 90% of maximum value, or time taken by the anode current to reach 10% of maximum value, or time taken by the anode to cathode voltage to decrease from 100% to 90% is known as delay time. If you draw the characteristics, this one is for gate current, and this one is for anode current, and this one is for VAK. Voltage across the switch. So this one is maximum voltage across the switch. Next, this one is maximum rated current. When the switch is on, maximum current flowing through the switch. And this one is maximum gate current. So it is 100% gate current and it is 100% anode current and it is 100% anode voltage. So here delay time is defined as the time taken by the gate current to reach 90% of maximum value. So if it is the 100% and this point is 90%. This one is 90%. So 90% means 0.9. 0.9 IC. So for anode current, delay time is defined as time taken by the response to reach 10%. Initially, for practical device, there will be some flow of current. That current is known as off-state current. So before turn on of the device, before applying gate signal also, there is a small leakage current. So here delay time is defined as time taken by the anode current to reach, this one is 100%. This one is 10%. Assume this one as 10%. This one is 10%. This one is 10% means 0.1 IA. 0.9, sorry, 0.1. It is 0.1 and it is 0.9. Next, in terms of anode to cathode voltage. In terms of anode to cathode voltage, initially, if the switch is under open condition, if the switch is under open condition, the voltage across the switch is maximum voltage. So once the gate current reaches 90% or anode current reaches to 0.1%, the voltage across the switch decreases to 90%. So this one is 90%. This one is 100%. Here, this line represents 100% and this line represents 90%. So in terms of anode to cathode voltage, it is defined as time taken by the anode to cathode voltage to decrease from 100% to 90%. And in terms of anode current, time taken by the response to reach to 10%. And in terms of gate current, time taken by the response to reach 90%. So that time is known as delay time. That time is known as delay time. This one is TD. Okay. So next, coming to rise time. First delay time completed. Next one is rise time. Rise time means time taken by the anode current to rise from 10% to 90%. If you take another line 100%, time taken by the response to reach 10% to 9%. This time is known as rise time. In terms of anode to gate current, time taken by the response voltage to decrease from 90% to 10%. This time is known as rise time. So, okay, any doubts?
No, sir.
Sir, time up.
Okay, okay. All of you leave this session. If you have any doubts, ask me.
Thank you, sir. Good evening, sir.
Okay, and thank you.
Thank you.